Today we're going to be talking about increasing and decreasing functions. And an increasing function is just what you might think it is. It's a function that is going up if you look at it graphically. Well, what does that mean algebraically? We'll talk about that in a moment as well. And decreasing functions mean just exactly what you think as well. It's going down. Could be going down like that or down like this. So how can we determine if functions are increasing or decreasing? Well, if you look at the examples that I've drawn up here, and let's kind of talk about tangent lines to these functions. And if you look at tangent lines, and I'm trying to draw up several here, what can you tell me all of these tangent lines have in common? They touch the function in one place, but all of them, the slope is a positive number. And if we go over here to the ones that are decreasing, whether it's this one or this one, at any place, what can you tell me about those? All of those have a negative slope. So that's an indication of whether a function is increasing or decreasing. And that's what we're saying right here. If we know that f is a continuous function and it's differentiable, and we've talked about those two things being quite a bit so far, if it's continuous and if it's differentiable, if the derivative is greater than 0, meaning if the derivative is positive on an interval, then f is increasing on that interval. That means the graph is going to be going upwards, either upwards like this, or it could be going upwards like this, but it's going to be going upwards. And if the derivative is less than 0, if the derivative is negative, then the function is going to look like one of these two graphs here. It's going to be going down as we look at it from left to right. And what about if the derivative is equal to 0? Then the function is constant. And those are the three cases that we can have with a function. A function, as we look at it from left to right, could be going up. The function could be constant, or the function could be going down. And in either case, by looking at the derivative, we can tell something about what the function is. So if you think about this in light of what we've already talked about with maxima and minima, suddenly you get the idea that we can draw a lot of information by looking at the derivative. We can determine a lot about what the graph's going to look like. So as we look for finding where functions are increasing and decreasing, these are the steps that we want to go through in order to do this. And these are things that you're going to be doing quite a bit the rest of the year. So I encourage you to really pay close attention here. Locate the critical points and use these as test points for a sign line. And we'll talk specifically about what a sign line is in just a moment. Now, how do we determine critical points? Remember, critical points are where f prime equals 0 or where f prime does not exist. So those are the places that we're looking for. Next thing we need to do is determine the sign of the derivative on each interval of our sign line. And then by that, we can look back at our three rules here and determine if it's an increasing or decreasing function on that particular region. So that's what we're going to be doing today. We're going to be learning to test to see whether this function's increasing or decreasing on specific intervals. And let's look at an example to help us determine this. Okay, find the open interval on which f is increasing or decreasing. First thing we need to do is make this problem a little easier. I made a mistake in creating it. And the last term needs to be a positive 5x to make it easier for us to work with here. Now, if we're going to find the open interval on which it's increasing or decreasing, we're going to find the derivative, which is 3x squared minus 8x plus 5, and set it equal to 0. Now, it is a quadratic, but it has a lead coefficient of something other than 1, so let's try and factor this by grouping. We need something that will multiply to give us 15 and add to give us negative 8. That'll be a negative 3 and a negative 5. So now we're going to separate out the middle term with those two numbers, and we'll say 3x squared minus 3x minus 5x plus 5 equals 0. If we factor out a 3x in the first two, we get x minus 1. Factor a negative 5 out of the last two, and we get an x minus 1. And now we can factor out the x minus 1, and we're left with 3x minus 5 equals 0. Now we should be able to solve that, and we find out that x equals 1 and x equals 5/3. So now what does that mean? That means that at those two particular points, the derivative is 0. Well, what does that mean for us? That means that at these two points the derivative is 0, so we expect it to be a maximum or a minimum. Now the next part we need to do is we're trying to determine if it's increasing or if it's decreasing. This is a very important concept here. And what we're going to do is we're going to create something called a sign line. And a sign line is simply a number line. And I'm going to label my number line F prime because in later problems we might have to do more than one sign line. And the first thing I want to do is put my two critical points that I have found on here. I'll put 1 and put 5/3. 5/3 is bigger than 1. It's important to have them in numerical order here. And now over here somewhere on the side I want to write out all of the factors of f prime. Since this sign line is f prime, we want to write out the factors of our derivative. Well, what are the factors? They're these things right down here. So I'm going to write them out like this: x minus 1 and 3x minus 5. And the way we want to envision this is that these two critical points break up our line into three distinct regions: region 1, region 2, region 3. And we know that at 1 the derivative is 0, and we know that at 5/3 the derivative is 0. Well, in each of these regions the derivative is either positive or negative. We've just got to determine which one. It's either positive everywhere in this region over here, or it's negative everywhere in this region. Well, how are we going to determine that? We're going to pick a number in this region. Pick a number smaller than 1, such as 0, for example. And if we put 0 in here, 0 minus 1, that's going to be a negative number. That's really the most important thing. We know that it's a negative number. And if we put 0 in here, we get a negative number. And these are factors. So in order to get the derivative, we multiply them together. A negative number times a negative number gives us a positive number. So that tells us the derivative is positive out here. Now we need to take a number between 1 and 5/3. Well, what's between 1 and 5/3? 5/3 is like 1.66. So we're looking at a number like 1.5. If I take 1.5 minus 1, that would give us a positive number. 1.5 times 3 would be 4.5. Minus 1 would give us a negative number. And if we've got a negative times a positive, we get a negative number. So that tells us the derivative is negative in here. And finally, out here we need a number larger than 5/3. Say 2, for example. 2 minus 1 is a positive number. 3 times 2 is 6 minus 5 is a positive number. And positive times positive makes this a positive number. So now by looking at our sign line, we can tell then that the function is increasing for all of these numbers out here. Well, how do we write that? That's from negative infinity to 1. Now how do we know it's 1? Remember, 1 is a critical point. What else can we say? We can say for these numbers in here, the function is decreasing, so f is decreasing from the number 1 to the number 5/3. Now notice I'm using parentheses here because these are open intervals. The function is not increasing at 1 and it's not increasing at 5/3. How do we know that? Because the derivative is 0 at those points, and when the derivative is 0, we've already determined it's a maximum or a minimum. We're not sure which yet, but we know it's one of those. And what's happening out here greater than 5/3? It's a positive. The derivative is positive. That tells us once again that the function is increasing. So the function's increasing from 5/3 to infinity. So we've determined what regions this function is increasing on and which regions it's decreasing on simply by creating a sign line and determining the sign, the positiveness or negativeness of the derivative in those particular areas. Alright, let's look at another example. Find the open intervals on which f is increasing or decreasing. Again, we're going to start off by finding the derivative. It's 3x squared minus 2x. Take the derivative, set it equal to 0. You're going to do that over and over all year long. 3x minus 2 when we factor out. So we get x equals 0 and x equals 2/3. Once again, we're going to do our sign line. It's important to label your sign line. It's f prime. We pick this critical point 0, this critical point 2/3. And now we've got our factors. We've got x is a factor and we've got 3x minus 2 is a factor. So now we simply pick a point in this region out here. What's a number less than 0? A negative number. So this will make that a -1. If we put -1 in up here, we get -3 minus 2, which again is negative, and negative times negative makes this a positive number. What about a number between 0 and 2/3? Maybe 1/3. 1/3 is a positive number, so x is positive. If we do 1/3 here, 3 times 1/3 is 1 minus 2 is negative, and a negative times a positive makes the function negative, so the derivative is negative here. What happens bigger than 2/3? What about, let's say, 1? Again, that's positive. If we put 1 in here, 3 times 1 is 3 minus 2 is 1, which is positive, and a positive times a positive makes it positive. So again, where is f increasing? F is increasing from -infinity to 0 and from 2/3 to infinity. And where's the function decreasing at? Is decreasing wherever the derivative is negative. So f is decreasing from 0 to 2/3. It's very important when you write these that you use the parentheses. This is an open interval. The points themselves, the endpoints are not in the intervals. Alright, this leads us to something else here, and before we go to the first derivative test, I want to take just a moment and look at this and see if we can determine something now. We know that the function's increasing from -infinity to 0. So let's take a moment and think about, what does that mean? The function's increasing. That means the function's got to be going up, right? And then what's happening at 0? Well, the derivative is 0, right? So that means that it's getting to a point. And what's happening from 0 to 2/3? The function is decreasing. So we know that the function looks something like this around 0. The function's increasing, then it's 0, then it's decreasing. And what happens at 2/3? We know that the function's decreasing to the left of it, and then when we get to 2/3, it goes back and it starts increasing. Now we don't know that the function looks exactly like this. I mean, it could be something that goes way up and then comes down just a little bit and goes back up, or it could be a multitude of different things. But one thing we do know is that at 0 the function is going to have to look something like this, and at 2/3 the function is going to have to look something like that. So what does that tell us about this point right here? At 0, what can you tell me about this point of the function? F has a maximum. Wouldn't you agree? Now it's not an overall max, because out here the function probably goes up higher, but it is a maximum in this area. And what's happening here? It has a minimum. At 2/3, f has a minimum. And again, that it doesn't mean it's the lowest it ever gets, but in that area that's the lowest that it ever gets. So suddenly, by knowing something about whether a function's increasing or decreasing, we know if it has a max or min. Because the function's continuous, the derivative has to go from being a positive to 0 to negative in this area here. Therefore, it has to be a maximum. And that's what the first derivative test says. The first derivative test says if we've got a critical point, and remember that means the derivative equals 0, and f is continuous, then it's a relative min, meaning it's the lowest point in the area if the first derivative goes from negative to positive. And that's the example that we've got in this picture right back here. Right here, the derivative goes from negative to positive, so that's a min. The other case being, it's a relative max if the sign changes from positive to negative. So again, back to this picture. It's going from positive to 0 to negative, so that's a relative max. And it's neither one if the derivative doesn't change signs there. So if the derivative were to, an example of C then would be, let's say the derivative were positive, then it's 0, then it's positive again. See, the derivative is positive, right in this area it becomes 0, but then it goes back positive. That's not a max or a min. But the example on the last slide gives us a relative min and relative max. This is one of those things that's crucial to know now, because suddenly we can figure out where the max and min are for a particular function simply by looking at the derivative. By looking at the first derivative, we can tell where the max and the min of a function are. So let's try to put that together now. Find the relative max and relative min for f on the given interval. So how do we go about solving this? We're going to find the derivative first of all. The derivative is the square root of 3 over 2 plus the sine of x. And we're going to set that equal to 0. You're going to do that one step there over and over with so many problems all year. Find the derivative, set it equal to 0. Now we got the sine of x equals negative root 3 over 2. So how do we solve that? Well, we're going to forget about the negative sign for a moment. When is the sine equal to the square root of 3 over 2? Remember the sign is left over 2 if you're looking at your left hand here. So if we do that, we get that the sine is square root of 3 over 2 at pi over 3. Okay, so we have pi over 3. Now remember, that's just a reference angle. At the pi over 3, the sign's a positive number. We don't want a positive number. We want the sign to be a negative number. Therefore, we need to look at quadrants 3 and 4, which are pi plus pi over 3, and 2 pi minus pi over 3. And if we work those two things out, we get 4 pi over 3 and 5 pi over 3. So that's where our derivative is equal to 0. Now we're going to do our sine line. Since we're given an interval from 0 to 2 pi, it's important that we put these on here as well, 0 and 2 pi. And now we've got 4 pi over 3, and we've got 5 pi over 3. And the spacing is not really important here. So now we've got 4 different regions to look at. And we've only got one factor for our derivative. We've got the square root of 3 over 2 plus the sine of x. And the square root of 3 over 2, the important thing to remember here is this number is a little bit greater than 1, because the square root of 3 is bigger than 2. I'm sorry, this number is a little bit smaller than 1. My apologies there. I said that incorrectly. This number is going to be a little bit smaller than 1. If you do it on your calculator, you'll find out that it's 0.866 and some numbers, I think. So now we're going to take a number in here between 0 and 4 pi over 3 that we know the sign of. So why don't we choose pi over 2 as our number in here? I'm just going to write it down so we'll know what we're looking at. The sign of pi over 2 is going to be the number 1. So we're going to have a positive number 1 plus this. It's going to make it positive. So that tells us the derivative is positive here. That tells us that this function is going up in this particular area. I'm going to just make a curve like that. Now we need to pick something between 4 pi over 3 and 5 pi over 3. What kind of number is that going to be? Well, what number is between 4 pi over 3 and 5 pi over 3? 3 pi over 2 is. Well, what's the sign at 3 pi over 2? Well, 3 pi over 2 is the same as pi over 2, except it's either positive or negative. We're not sure which. Well, this was a positive 1, so 3 pi over 2 is 1. Now, is it positive or negative? Where is it? It's between quadrants 3 and 4, so the sign's negative. So now we've got this number, 0.866 minus 1. It's going to make this a negative number. So that tells us that the function is decreasing here. All right? And then when we get to 5 pi over 3, we know that it's at 0 again. What else is going on out here? Let's pick a number larger than 5 pi over 3 to put in here. Maybe 2 pi itself even, okay? If we put 2 pi in here, 2 pi would give us a sign of 0. So root 3 over 2 plus 0 makes this a positive number. So then this is a positive. So that means our function's going up here. So what do we know then? What's happening at 4 pi over 3? The derivative is going from positive to negative. So at 4 pi over 3 is a max. And what's happening at 5 pi over 3? The function is decreasing, then it becomes 0, then it goes back to increasing. So it's a min at 5 pi over 3. And this is just a good way of knowing where the max and min occur. Now we don't know exactly where, we don't know exactly what the function value is, but we know whatever that function value is, it's the largest in the area. Let's take another example. Find all relative max and relative min for this function. Again, find the derivative. F prime of x, it will be 3/5 x squared minus 9 to the negative 2/5 times the derivative of the inside, 2x. And we're going to set this equal to 0. Well, if I take this 2 and multiply it by 3/5, that gives me 6/5 times x over x squared minus 9 to the 2/5 power. Now this should kind of make us think here. Okay, we've got a fraction equal to 0. We know 6/5 is not going to be equal to 0, so let's just kind of forget about that. When's a fraction equal to 0? When the numerator is equal to 0. So x equals 0 is a critical point. But now we've got a fraction. So that means that the denominator cannot equal 0. So that means when x is plus or minus 3, the denominator is 0. So these are also critical points. So we have 3 critical points here. 0 because that's when the function's 0. Plus and minus 3 because that's when the denominator is equal to 0. That's when the function's undefined, or the derivative is undefined. So let's go back now and let's look at these 3 critical points. So we've got negative 3, we've got 0, we've got 3. Okay, our derivative, I forgot to label it. Our derivative is 6/5 is one thing. Now I'm going to go ahead and write down plus for all 4 regions because 6/5 is just a constant number, so it's always going to be positive. I'm going to write down x because that's our numerator, and then I'm going to write down x squared minus 9 to the 2/5. Okay? Alright, so this is always a positive number. What about x? When I put negative 4 in here, I'm going to get a negative number out. And when I put negative 4 in up here, I'm going to get 16 minus 9. That's a positive number, right? And if I take the 5th root of it, it's still going to be a positive number. And if I square it, it's still going to be positive. So suddenly I've got a positive number out of here. Positive times negative times positive means that the overall derivative is negative. So the function is decreasing here. What's happening between negative 3 and 0? Let's put negative 1 in here. Well, that's still negative. Negative 1 squared is going to be 1 minus 9. That's a negative number. The 5th root of that will still be negative. We can take the odd roots of a negative number, but when we square it, it's going to go back to positive again. So the overall sign of the derivative is a negative again. A positive times a negative times a positive. What happens when we put 1 in here? Well, that's going to make that a positive number. and 1 squared minus 9, we get the same thing as we did before, a positive again. But this time we've got 3 positives, so the derivative is positive there. That means the function's going up. And what about when we put 4 in? Well, that's obviously positive. 4 squared minus 9, that's a positive number, so it's going to be positive overall. So now we know that this function is decreasing out here. Then it goes to 0, then it's decreasing again, then it goes to 0, then it goes to increasing, goes to 0, and goes to increasing. So what do we know? Well, the only sign change for the derivative occurs right here. So we know that x equals 0 is either a max or a min. Which is it? Well, let's take a moment and draw out what's going on here. We know that here the function is going from negative, the derivative is decreasing, the derivative is negative, then it's 0, then it's positive. It goes from decreasing to 0 to positive. Therefore, what does that look like? X is a min. So that's a minimum. Now, what does the function look like over here? Well, the function is going up, then it becomes 0, then it keeps going up. So that's not a max or a min. And what's happening over here at negative 3 is going down. It goes to 0, then it goes back down. Again, it's neither a max nor a min. So suddenly we can figure out a lot about this function. I mean, we can almost take these 3 green pieces that I've drawn and kind of splice them together and have a pretty good indication of what this function is going to look like. But the main thing is we've got a minimum at 0, negative 3, and 3 are neither, they're critical points because they're candidates, but they're not a max or a min. Find all relative max and min for this function. Now this is a curveball, and really first thing you want to do is take the derivative, obviously. Now there's an easy way and there's a hard way to do this. You can use the quotient rule here, or I can rewrite this function to begin with. If I rewrite this function as x to the 4th over x squared plus 1 over x squared, suddenly that first thing just becomes x squared, doesn't it? And that second one I can write as x to the negative 2. Now I think taking the derivative of this thing out here is far easier than the original function. It'll give us the same thing in the end. So if we take that derivative, we get 2x minus 2x to the negative 3. So we've got the derivative, we're going to set it equal to 0. What happens now? We factor. Well, how can we factor? This has got a 2 in common, but what about the x's? Both of them have x's. What can we factor out? We can factor out the lowest exponent we see, x to the negative 3. And if we factor that out, what are we left with? Well, x to the negative 3 times what would give us x? That's going to be x to the 4th minus 1. Excuse me, plus 1, I'm sorry. Plus 1. Negative 2, x to the negative 3. This gives us x to the 4th plus 1 equals 0. Well, what do we do now? Well, if we try to solve this out now, this thing out here being 0, negative 2 is never equal to 0. X to the negative 3 equals 0. What does that mean? That means 1 over x cubed equals 0. Well, 1 can never be 0. But x equals 0 is a critical point because the derivative is undefined there. So we've got a critical point at 0. Well, what about x to the 4th plus 1 equals 0? Well, let's think about this for a second. We're taking a number and raising it to the 4th power. So that's going to be a positive number, or 0, right? Then we're going to add 1 to it. That's going to make it a positive number. So this is never equal to 0. So we've only got one critical point. We've got a critical point at x equals 0. So let's draw this out and see what's going on here. Here's at x equals 0. Our derivative is what? Negative 2x to the negative 3 and x to the 4th plus 1. Don't forget to label. What happens when I put a negative number in here? I get negative and I get positive. Therefore, the derivative is negative here. Excuse me, I'm going to get positive here, aren't I? Because if I put a negative number in here, that'll be negative, times the negative 2 makes it positive. So the function is positive there. What about when I put a positive number in there? What if I put 1 in? Again, that's going to be positive. And if I put 1 in, that'll be a positive number times negative 2, makes it negative. So the derivative is negative. So this function is up, and then it's down. So at 0, it looks like it's a max, right? That would be your first thought. X equals 0 is a max. Well, what happens if we put 0 in the original function? We get a 0 in the denominator, right? So remember, if you go back and look, to be a critical point, the function has to be defined at that point. F is not defined. F is not defined at 0. Therefore, it's not a critical point. Therefore, we'd have no max or min. Okay? And yes, I did know that that was going to happen before I did all this work. What I wanted to do is go through the work with you just as practice, but also to remind you that you always got to go back. Is the function defined at that particular point? We can't put 0 in the original function, so it cannot be a maximum there. Since 0, when we put 0 into the function, we get a 0 in the denominator. That tells us that we have what for this function here at 0? That we're going to have a vertical asymptote at x equals 0 for this particular function. So there's actually not a max or not a min for this particular function. Well, you've got a homework set to do with this as well now. So I encourage you to go through and do that. And remember, take the derivative, set it equal to 0, and then do a sign line. Those are the most important things for you to remember out of this lecture today.